All right, let's talk about a very important family of functions, polynomials. Why would we care about polynomials? Because you can use polynomials for modeling any function or many types of functions. All right, so just some definitions. A polynomial of degree n is a function of this form, and this is called the leading term. A sub n is the leading coefficient, and the last term, which is a constant, is the constant term. So the most important thing about a polynomial is the degree of the polynomial. What does the degree tell you? Well, one of the things that the degree will tell you is the end behavior, which is what happens as x goes to infinity and x goes to negative infinity. So if your polynomial has an odd degree, then the ends go in the opposite direction. And if the polynomial has an even degree, then the ends go in the same direction. So let's look at some polynomials. All right, so for this polynomial, is the degree even or odd? If you said odd, you would be correct. And one of the features of a graph of a polynomial with an odd degree is that it has no maximum and no minimum if you use the entire domain. It has a relative maximum and a relative minimum. So it's a maximum in its little neighborhood, but the maximum of the entire function is higher. And that's going to be true of all polynomials with an odd degree. All right, is this one even or odd? If you guessed even, oops. If you guessed even, you guessed correctly. And you'll notice that this function has a minimum, but no maximum. All right, what about this polynomial? Is the degree even or odd? If you guessed even, you guessed correctly, and you'll notice that this function has a maximum, but no minimum. And this will be true of all polynomials with even degree. They'll either have no maximum because both ends point up, or no minimum because both ends point down. All right, suppose you plug 5 into a polynomial and it's equal to 0, then x equals 5 is a solution of setting that polynomial equal to 0, which is how you solve polynomials. Then x minus 5 is a factor of that polynomial, and x equals 5 is an x-intercept of the graph of p of x. This is probably easier to think about if we do a particular example. So let's start there. All right, so suppose we're given this polynomial in factored form, meaning it's written as a product of its binomial factors. Binomial just means there's two terms. All right, so which values of x make this polynomial equal to 0? All right, so you can probably do this in your head, but if you can't, just take each factor and set it equal to 0. So the values of x that make p of x equal to 0 would be x equals 5, x equals 1 and x equals 2. So we're going to have x-intercepts at the following values of x. So let's just go ahead and draw the graph of this polynomial. And before we forget, what would be the degree of this polynomial? Well, if you would multiply it all out, the highest degree would be x cubed. So this is a degree 3 polynomial. So would the ends go in the same direction or in opposite directions? If you said opposite direction, you would be correct. So we know that the zeros of this function are going to be at 1, 2, and 5. So a polynomial is going to be a wiggly graph, and it's only going to cross the x-axis in these 3 places because there's no other value of x that makes this polynomial equal to 0. So we can think of it as divided up into regions. So we have 4 regions, and because the graph of the polynomial only crosses at these 3 points, those are the only 3 places where the polynomial will change sign from positive to negative or negative to positive. So to draw the graph, we can just take these 4 regions and test any point in those regions in our polynomial and see if it'll make it positive or negative. So if we take a point over here, like 0, and plug it into our polynomial, so 0 minus 5 is going to be negative, 0 minus 1 is going to be negative, 0 minus 2 is negative, a negative times a negative times a negative is going to be negative. So I know my graph is going to be negative in this region. And then between 1 and 2, we could plug in, say, 1.5. And we don't need the precise number. We just need the sign of each factor. So if I put positive 1.5 in here, that'll be negative. Positive 1.5 in here, that'll be positive. Positive 1.5 in here will be negative. So a negative times a positive times a negative is going to be positive. So in between 1 and 2, the graph is positive, and then it goes back to 0. Between 2 and 5, let's pick any number like 3. If I put 3 in here, it'll be negative. Put 3 in here, it'll be positive. Put 3 in here, it'll be positive. A negative times a positive is going to be negative. So the graph is going to be negative between 2 and 5. And then pick a point, a number greater than 5, like 6. 6 minus 5 is positive. 6 minus 1, positive. 6 minus 2, positive. A positive times a positive times a positive, positive. And then if you wanted to be really precise, you could plot this actual point about halfway between to get the y value. But really, we just want the general shape. All right, let's try another. All right, try drawing the graph of this function. So first of all, you notice that this factor is squared. So that's going to change things a little bit. And before we even start, let's think about what the degree of this polynomial is. If you said degree 4, you would be correct. So will the ends go in opposite directions or in the same direction? If you said same direction, you would be correct. All right, let me get started here. Let's identify the zeros of the polynomial. So those are the numbers that make each factor equal to 0. So that would be x equals -2, x equals +1, and x equals +3. And then let's think about this squared term. All right, one feature of a number that's squared, if you square a positive real number, you get a positive. If you square a negative real number, you get a positive. So that might be a hint as to what this factor is going to look like when we do the graph. And I like to just put these little imaginary vertical lines to help us visualize that there's 1, 2, 3, 4 regions. So we need to check the sign of the polynomial in each of these 4 regions. So we take a number in this region, like -3. So -3 minus 2 is going to be negative. -3 minus 1 is negative, but then when you square it, it's going to be positive. -3 minus 3 is negative. So when we plug in -3, we get a negative times a positive times a negative, which is positive. So the graph is going to come down this way. All right, between -2 and 1, we pick any number like 0. 0 plus 2 is positive. 0 minus 1 is negative, but squared is going to be positive. 0 minus 3 is negative. So positive times a negative is negative. So the graph is going to be below the x-axis for this region. And then between 1 and 3, we could plug in 2. 2 plus 2 is positive. 2 minus 1 is positive, and then you square it, that stays positive. 2 minus 3 is negative. So positive times a negative is negative. All right, so now I need to fix my graph because polynomials don't have corners like that. So it's going to be negative and then negative again. All right, so negative, 0, and then negative. Make it nice and smooth. You can probably already guess what happens here, but let's check. Let's plug in 4. 4 plus 2 is positive. 4 minus 1 is positive. Squared stays positive. 4 minus 3 is positive. So positive times a positive times a positive is positive. And it's the degree 4. They go in the same direction. So that verifies our expectations. So this graph is going to have a minimum, one of these two, but no maximum. Let's do another. All right, I think you're ready to try this one on your own. And be sure you pay attention to this leading coefficient of -2. That'll affect your graph. All right, first of all, let's look at the degree of this polynomial. So it's 1, 2, 3, 4, 5. So do the ends go in the same direction or opposite directions? You said opposite, that would be correct. Well, let's draw my axes. All right, then we want to plot the zeros of the polynomial. So that's going to be x equals -3, x equals 0, x equals 1, and x equal to 4. And I'm going to put some little vertical lines just because it makes it easier for me to look at. All right, how many regions do we need to test? 1, 2, 3, 4, and 5. And don't forget about that -2 out front. All right, so if we put in a number that's less than -3, like -5, so I'm just going to put that -2 into my sign chart. So that's always negative. -5 plus 3 is negative, but then when you square it, that's going to be positive. -5 is negative. -5 minus 1 is negative. -5 minus 4 is negative. So if you have a negative times a positive times a negative, 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 all of that's going to be positive. Let's pick a number between -3 and 0, like -1. So I'm just going to put a negative for that -2 so don't forget it. -2 plus 3 is positive. The positive squared is going to stay positive. -2 is negative. -2 minus 1 is negative. -2 minus 4 is negative. So I have 4 negatives multiplied. That's going to be a positive. Between 0 and 1, we could put in 1/2. So I'm not going to forget my -2. I'll put that down here. 1/2 plus 3 squared is positive. 1/2 is positive. 1/2 minus 1 is negative. 1/2 minus 4 is negative. So the whole thing is going to be negative in this region. Between 1 and 4, I'm going to put in +2. So my -2 is negative. -2 plus 3 squared is positive. 2 is positive. 2 minus 1 is positive. 2 minus 4 is negative. So the whole thing's going to be positive. And then greater than 4, once again, my leading coefficient is negative. 5 plus 3 is positive. Squared stays positive. 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 So the whole thing's going to be negative. All right, so it stays positive on either side of this 0, and that's because that's a squared factor. By the way, that's called multiplicity 2. I'll write that down in a second. So it's going to be positive, 0, and then positive again. And then here it changes from positive to negative. And then from negative to positive. So the ends go in opposite direction. So this function has no maximum and no minimum. It does have a local maximum, a local minimum, and a local maximum. if one of your factors is squared, it's said to have multiplicity 2.